Welcome to homework.
Once again, welcome to a new problem. This time we're still on wavelengths. It so happens that there's light, and this light has wavelength lambda. This is the information that's given. We have a slit. We have a slit, and on the opposite side of the slit, we have a screen, obviously, and we're always going to have this central maxima on the screen right there. And there are two adjacent maxima that happen at different angles. The first one happens at sine theta equals to 0.2, and then the second one happens at an angle of sine theta equals to 0.3. Obviously, the fourth order maxima, m equals to 4, is missing. So that's absent from the screen. And the requirements of the problem, remember, if you have light going in, then there is diffraction taking place, and there's going to be angles theta that the light can travel. So part A of the problem is we want to find D, which is the gap between slits. So we want to find that. And then the second thing is that we want to find, in part B, we want to find the smallest slit width. And of course, if you can recall, the slit width is this portion right here. We're calling it A. So this is A. That's what we want to find out. The smallest slit width that we can have. And for this width, for this slit width, we're going to continue on part C. We'll get the largest values of the order number m of the maxima produced by grating. And then in part D, we want to find the second largest value. Obviously, it's the values of the number of the maxima produced by the grating. And then, of course, in part E, we want to find the third largest. So those are the requirements of the problem. We're looking at finding D, which is this gap between the two slits. And then we want to find the smallest slit width, which is A, obviously. And then after that, we have three other parts to the problem where we want to find the largest, the second largest, and then the third largest values of the order number m. M is our order number of the maxima produced by the grating. So we're just going to go ahead and jump onto the next page. And it so happens that we have conditions for diffraction, and the condition for maxima, this is part A. Okay, in part A, we're saying the condition for maxima. In part A, we're saying condition for maxima is d sine theta equals to m lambda. We know that D is a slit separation. This is a slit separation. And then we also know that lambda is the wavelength. We already listed lambda as being 600 nanometers. That's our lambda. And then theta is the diffraction angle. You want to call it the diffraction angle. Theta is the diffraction angle. So sine theta is true when m equals to for m, and then sine theta, when sine theta is 0.3, we have m plus 1. Remember, m is the order. So for this one, that's the first m, and then the next one is m plus 1, since they're adjacent. Okay, so we're going to go ahead and have use this formula right here and say d sine theta 0.2 equals to m lambda, and then d sine theta, which is 0.3, equals to m plus 1 lambda. So those are the two parts to the problem. We can call this equation 1, and we can also call this equation 2. It's easier to jump into the next page to see how we solve these problems. So we'll say we're going to subtract equation 2 from equation 1. So let 1 minus 2. Remember, 1 is the first equation. So we have d 0.2 minus d 0.3 equals to m lambda equals to m lambda minus m plus 1 lambda. You could actually do it the opposite way, so you could have done d 0.3 minus d 0.2 equals to m plus 1 lambda minus m lambda. You could have done that. It's still appropriate. In fact, it's easier that way, since we're ending up with 0.1 d equals to, if you use distributive property on this one, you see we have m lambda plus lambda minus m lambda. These two cancel out, so 0.1 d becomes equivalent to lambda, and that means that we can solve for d by dividing both sides by 0.1. So d is equivalent to lambda over 0.1. We're not done yet, because we do know that lambda is 600 nanometers, so we'll use that, change it to meters. 1 meter is 10 to the 9 nanometers, and then we want to divide that by 0.1. And so our final solution for d is the same as 6 times 10 to the negative 6 meters. 6 times 10 to the negative 6 meters. So that's our d in the next part of the problem. That's part B. We wanted to find A, which is the minimum slit width. So this is part B. We know that since the fourth order is missing, we can say d over a, that's the ratio, equals to 4. So a equals to d over 4. We already have the value for d. 6 times 10 to the negative 6 meters divided by 4. And so final answer is the same as a equals to 1.5 times 10 to the negative 6 meters. That's our A. And then in part C, we have the condition for maxima is d sine theta equals to m lambda. And so, the max value of m happens when theta is 90. And so m maximum equals to d over lambda, which becomes 6 times 10 to the negative 6 meters over lambda, which is 600 times 10 to the negative 9 meters. the so what happens is we can't observe diffraction when theta is 90. I mean, that makes sense because, I mean, think about it. If this was a slit and then the light is coming through at an angle, then you can always see the diffraction. But then if the angle is 90, like, it becomes almost flat. So you don't, you can't see the diffraction. And so, you know, the max diffraction we can observe is, and this is the diffraction pattern we can observe, is when m is less than d over lambda. So that means m is going to be less than 10. You know, remember this solution to this one was 10, so m has to be less than 10. And so the maxima, you know, the maximum value for m has to be 9. Maximum value for m has to be 9. Remember, condition for maxima is d sine theta equals to m lambda, and the maximum value happens when theta is 90. So if you do the computations, you get 10, but then it follows that you can't observe the maxima when theta is 90, so it has to be less than that, so m has to be 9. That's part C. The final, in part D, we'll jump onto the next page. D, we want to find the next largest order. Next largest order. So 9 minus 1 gives us 8. The fourth order is missing. So, and that's the fourth order maxima. The fourth order maxima is missing. And so also 2 times the fourth order is the 8th order. So that means the 8th order is also missing. The 8th order is also missing. And so the second largest order will be m equals to 8 minus 1, which is m equals to 7. That's the second largest order because the 8th order is missing since the fourth one is also missing. And then the final part of the problem, which is part E, we want to find the third largest. And the third largest, since we already have the second largest being 7, so the third largest will just be 1 less than that. So the third largest maxima will be m equals to 6. So again, you know, we had a problem here. We're given the wavelength 600. We had to find D, which is the gap between the 2 slits. We also had to find A, which is the smallest slit width. And then after that, we had to find the largest, second largest, and third largest values of M. With the understanding that sine theta is 0.2, that happens at M and M plus 1. So we came up with 2 equations from the condition of maxima, subtracted them from each other, and found that D was 6 times 10 to the negative 6 meters. And then the ratio D over A is 4 because the fourth order is missing. So A becomes D over 4, and that was 1.5 times 10 to the negative 6. And then we moved ahead and had the ratio D over lambda to help us get the maxima M, which is 10, assuming that theta is 90. But since you can't have diffraction at an angle of 90, you have to go less than that. So M becomes 9. And then after the 9, we have the next largest, which is 8. But this is a contradiction because the fourth order is missing. So that means the 8th order also is going to be missing since 2 times 4 is 8. So we subtract 1 from 8 and get M equals to 7. And then finally, the third largest is the one adjacent to the second largest. So 7 minus 1 is 6. So hope you enjoy the problem. Feel free to send any questions or comments and have a wonderful day.